Okay, chapter 1, section 5, equations. So in this section, we're going to talk about solving linear equations, solving quadratic equations, and then other types of equations. So some simple definitions first. So the value of an unknown that makes an equation true are called solutions. Also, we refer to them as roots of an equation. And the process of finding solutions is called solving an equation. Okay, obviously. Two equations with exactly the same solutions are called equivalent equations. And to solve an equation, we try and find simpler equivalent equations in which the variable stands alone on one side of the equation. Okay, so pretty obvious things. So some basic properties that we get to use when we're trying to solve equations. I'm sure we've used these a lot, so you should be comfortable with this. If we have one equation, A equals to B, then this little double arrow symbol means that it is equivalent to this other equation, where all we've done is add the value C to both sides, right? So this first property is just indicating that you can always add the same constant to both sides of the equal sign and maintain that equality. You know, you get it. If you start off with a true statement, we can add C to both sides, and we'll be able to get another true statement. The other property that we get to use is that if we multiply both sides of the equal sign by some constant C, then again we end up with something else that's also equivalent. Okay, and that's so long as C does not equal to 0. The reason we do that is because if we multiply both sides of the equal sign by 0, then you could potentially take something that isn't true and make it true, right? So for example, 3 does not equal to 2, right? That's definitely a lie. Does not equal. But if we choose to multiply both sides of the equal sign by 0, right? If that's what we choose to do, multiply both sides by 0, we end up with 0 equals 0. And that is true. So we start off with something that's false, and then we introduce this product of 0 on both sides of the equal sign, and we end up with something that's true. So in that sense, we have to be careful not to do that. That's why we can't multiply both sides of the equal sign by 0. We have to be careful. Okay, solving linear equations. So to start off with, when we're working with linear equations, a linear equation is something of the form ax plus b equals to 0, or something equivalent to it. And this is where the a and the b are both real numbers, and the variable we're solving for is x, right? Or something that fits this form. So here's some examples. So linear equations, here's some examples of linear equations. So linear equations could take on any one of these forms, where we have x to the power of 1. That's all that really matters. Then we have some constant, we have another constant. So we can use algebra to manipulate this to get it to fit the form of a linear equation as defined here. Right? That's really the point. Okay, so those are linear equations. Right? Every one of these is linear equations. The powers of the variable is power 1, degree 1. And even after you simplify and distribute and whatnot, you're still going to end up with power 1. So we have to be careful about cases where, after a multiplication, we might end up with a power 2 or something. Okay, this one is not a linear equation because of this quadratic. This one is not a linear equation because of the root, right? Square root of x. This one's not a linear equation because of the degree to the power x, right? It's in the denominator. So this, as we saw earlier, is equivalent to raising this to the power of -1, and that's not linear, right? We need the power to be 1. So these are all non-linear equations. Okay, so how do we solve linear equations? Well, I'm sure this is very familiar. We get to use our property that whatever operation you do to one side, you must do to the other, therefore maintain the equality. Okay, so we want to undo this, right? So we get to introduce an addition or a subtraction or a multiplication or a division of any constant as long as we do the same operation to both sides of the equal sign. So in this case, I'm going to put some space there, 3x plus 8. Of course, we would add 4. As long as you add 4 to that side, you also add 4 to this side. Then you arrive at, so we end up with 7x minus 4 plus 4. So minus 4 plus 4 becomes plus 0. And then on the other side, we end up with a plus 8 plus 4. So we end up with 3x plus 12. So we're getting a little closer to solving for it. Plus 0. Anytime we're adding 0, you're not changing anything. So we can just eliminate that 0 and leave it as a 7x equals to 3x plus 12. And now, again, I'm going to put a little bit of space there. And focusing on isolating the variable x on one side, what I want to do is subtract 3x from this side, since I know that that'll make it 0. Therefore, I also subtract 3x from that side. And then we still have that plus 12. Doesn't disappear, I just brought it down. So here I added 4 to both sides. Here I subtracted 3x from both sides. Hopefully this is really, really easy. So 7x minus 3x is going to end up equal to 4x. So this will be 4x equals 2. And now these guys, we have 3x minus 3x. Again, these will turn into a 0. And then plus 12. So then we have 4x equals to positive 12. 12 plus 0 is just 12. Now, in this stage, you can either multiply both sides by the reciprocal of this factor, the 4, or you can divide both sides by 4. They both mean the exact same thing. So I'm going to multiply this side by 1 divided by 4, because I know that that will reduce to 1. Whatever operation you do one side, you must do to the other. So I'm going to multiply the other side by 1/4. So now I know that these guys, let's put it in green, these guys will cancel, right? We can put a little 1 underneath the 4. The 4's cancel, giving me just 1. 1 times x equals, 4 goes into 12 3 times. Put a little 1 here. 4 goes into 12 3 times. So I end up with 1 times x equals 3, or just x equals to 3 as my final solution to this thing. Okay, I know I went and did way too many steps, a lot more steps than you guys probably need to see. I just wanted to be really, really redundant this first time around. I don't expect you to do this much or show this much detail when you do your work. It's fine. I just wanted to make sure we were all on the same page this first time around. But I know that most people are very comfortable with a little less work being shown, and I'm okay with that. So let's just repeat it with the kind of work that I think most people are happy with. So instead of this whole process of adding 4 this way and bringing down as a 0, most people are just happy just putting like a plus 4 like that and a plus 4 like that, and then we add it. And then so these guys cancel, and then you bring it down as 7x plus 0, or just 7x, equals to 3x plus 12. And then maybe subtract 3x, and then again we end up with a 7x minus 3x, which then just becomes positive 4x. And then these guys cancel. So equals 12. And now, again, we can either multiply both sides by 1/4, or we could divide by 4. Either way, right? Dividing it by 4, multiplying by 1/4, same thing. Divide by 4, divide by 4. And then you can just cancel out the 4's, and we end up with x equals 3. Good. So, easier, faster, that's okay. So I just wanted to point out the technical reasons for why some of these steps are possible. And some people take even more shortcuts, and that's okay, but there is a sort of a limit. At some point, I think some people take so many shortcuts that maybe they lose track of what they're doing and get a little confused. So it's just kind of up to you to decide if you're really crystal clear, and if it's really crystal clear in your head why you're doing things and how, what the rules are. And then, of course, in terms of a test or something, you have to give me enough information, enough work to convince me that you know what you're doing, right? When the test comes along, keep in mind that I'm interested in you convincing me you know the answer, not necessarily in finding the answer, right? So just saying, if I gave you this on a test and you just wrote down, oh, the answer is 3, you're not going to get any credit, right? I'm not asking you to find the answer. I'm asking you to convince me that that's the answer, and just simply putting down the answer as 3 is not going to be good enough, right? So you got to have that balance. You don't want to show too much work and get pretty daunting to write all that, especially as the work gets harder, as these equations get harder. You're sort of expected to do some of this stuff in your head, and then this sort of shortcut is great to condense the writing that you have to do. Okay, so x equals to 3. Once we have x equals to 3, it's always a good idea to check it. So why don't we check it? Let's put it over here. Check. If it's in fact true, it must be the case that 7 times something minus 4 equals to 3 times something plus 8. And that something, we think, is that 3, right? Let's check to see if x equals to 3 works. If that's the answer, it should be the case that the left side equals the right side. We should get a true statement. And so we end up with 21 minus 4 on the left-hand side. And on the right-hand side, we end up with 9 plus 8. 21 minus 4 is equal to 17. And on the right hand, 9 plus 8 is 17. True statement, it worked. We found the right answer. Okay, so x equals to 3 is the only solution to this equation. Here's what the author wrote. Similar to my first method of kind of showing every step, I think that's just because it's early on in this chapter. We just want to introduce a couple of exercises where we really show all the little details, and then pretty quickly we move on to some of the more shorthand notation. Okay, but same idea, same principle, and x equals to 3 is the same solution. Plug it in, check our answer, we get 17 equals 17. Okay, moving on. Solving quadratic equations. So quadratic equations, as opposed to linear equations, are equations that are degree 2. So here are linear equations. Linear equations have a first degree, so maybe something like this, or maybe something like that. These are linear equations. But quadratic equations involve a variable where the highest power in one of our variables is 2. Polynomial of degree 2. It's a quadratic equation. So here's a couple of examples, maybe this one or this one. A quadratic equation is an equation of the form ax squared plus bx plus c equals to 0, where a, b, and c are real numbers, or something equivalent to it, right? We can manipulate it, as you can see up here. It could be something that fits this form or this form. Either one of those are quadratic. We can easily do a little bit of arithmetic to manipulate this to make it fit that form there. Okay, but the standard way in which we present it is going to be to set it equal to 0. Okay, and so the coefficients could be any real numbers except a is not allowed to be 0, because if it was 0, then we'd have an easier equation, right? 0 times anything is 0. This term would disappear, and we'd be back to a linear equation. So that's for that reason we don't allow it to be 0. Okay, when we want to solve quadratic equations, we often use this zero product property. The zero product property is simply pointing out that if we have two unknown values, if two things are being multiplied, like a times b equals to 0, it can only be true, this can only happen if one of them, at least one of them, is a 0. The a must be a 0, or the b must be a 0, or maybe they're both zeros. But at least one of them must be a 0. That's the zero product property. And there's something very special about the number 0 is the only one for which this is true. 1 is always, people always make a mistake with 1. So note that A times B equals to 1 doesn't let you conclude anything about A or B, right? People think, oh, well, does that mean at least one of them must be a 1 or they're both 1s? And that's not true. There could be lots of situations where blank times blank equals 1. It could be 4 times 1/4, that equals to 1. It could be -1 times -1, that equals to 1. Right? So there's all kinds of numbers that can go into either one of these and maintain a true statement. So there's really nothing special about the number 1. But there is something special about the number 0. If we're multiplying two things, and I know for sure that the answer is 0, then I can conclude that at least one of them must be 0. There's no way to multiply two numbers where neither is 0 and somehow the final answer is 0. Right? So that's a very special property of the number 0. So when we have x times y equals to 0, we can conclude that either the x is a 0 or the y is a 0. If we had something a little more complicated, like x plus 2 times y minus 7 is 0, then again, since we're treating this as a little unit, a little binomial multiplied by another binomial, then again we can conclude that either this guy is a 0 or maybe this guy is a 0. Right? That's the power of this. So we can take something that looks a lot more complicated and separate it into two sort of smaller pieces, and allows us to solve quadratic equations or other types of equations this way. Okay, so let's jump into an example. Let's say we want to find the real solutions to this equation. So the first thing we'd want to do is set it equal to 0. So let's move this over to the other side. I'm going to rewrite it over here. X squared plus 5x equals to 24. So I'm going to subtract 24 from this side, subtract 24 from the other side, and right underneath it. Notation is also really important. A lot of people still have this habit of going this way, equals x squared plus 5x minus 24 equals 0 equals x, right? Like going this way. And that is really, really difficult to follow. I mean, you might be fine. I know I talk to students and they're like, oh, I can follow it. Yeah, well, maybe you're fine, but I have a hard time following it, and others will too. It's a good habit to start writing it this way, with the equal sign neatly right underneath it. And as these things get more and more complicated, which they will, I promise, it becomes more and more valuable to keep really nice, neat notes. Anyway, so we subtract 24 from both sides. So we get a 0 on the right-hand side. And on the left-hand side, we don't have like terms, so we end up with 2x plus 5x minus 24. Okay, so now our goal is going to be to factor this guy so that we can use the zero product property. So luckily, this factors nicely. Since there's a nice 1 out in front, I know that it's going to be something of this form. X plus this equals 0. Two numbers that multiply to negative 24 but add to 5, so now it just becomes a guessing and checking method. Numbers that multiply to 24, there's like 12 times 2, that gets me to 24. But they add up to 14, or if one of them is, we need one of them to be negative. So let's say negative 12 times 2, that's going to be negative 24, right? Negative 24. But then they add up to negative 10, and that's not what I want. And even if I move the negative to the other side, they would add up to positive 10, so that's not going to work. How about 6 and 4? 6 times 4 gives you 24. And if we make one of them negative, we'll get the negative 24. But again, that's not going to give me the result I want. So how about 8 and 3? 8 times 3. If I make the 3 the negative, I'll get negative 24, and they add up to 5. Good, found them. So this will be an 8, and this will be a negative 3. So I can rewrite this once again as x plus 8, x minus 3 equals 0. And now I'm ready for the zero product property. I have two things being multiplied, and the answer is 0. which means either this guy is 0, x plus 8 equals 0, or maybe this guy is 0, which is x minus 3 equals to 0. If I subtract 8 from both sides, so minus 8 minus 8, I get x equals to negative 8. X equals minus 8. And then if I add 3 plus 3 plus 3, then we end up with x equals to positive 3 on the other side. Okay, so we get two solutions. It's either this one, or maybe both. We have to check them. Okay, so now we got to go back to the original equation, and let's test them to see if replacing the x value by these results will give me what I want. Let me erase this. I need this. So x equals to negative 8 is one of them. So I have blank squared plus 5 times blank equals 24. And I'm checking if, in fact, the negative 8 is one of the answers. Minus 8, minus 8. So minus 8 squared, that's going to be 16. I'm sorry, 64. Negative 8 squared is 64. And then 5 times negative 8 is going to be minus 40. And yep, that does in fact equal 24. So negative 8 was fine. That is definitely a valid substitution that gives you a true statement. So let's check the other one. How about x equals to positive 3? Let's check that one. So we have blank squared plus 5 times blank equals 24. And we're going to check if, in fact, replacing the x value with a 3 is going to give us a true statement. And so we get 3 squared, which is equal to 9, plus 15. And yep, that does, in fact, give you 24. So both of them are true. Good. So we have two valid answers for our quadratic. Okay, so this is a good example of using the zero product property. We're given something, a polynomial to solve. Step one is to move everything to one side, so we have the 0, right? Because the zero product property only works when one side equals 0. And then our goal then is going to be to rewrite the other side as a multiplication so that we can use the zero product property and separate it into easier portions. All right, so moving on. Here's what the author did. Same thing. Moved the 24 over, factored it just like we did. Equals 0. Breaks it down in two pieces. Checked it. Awesome. Okay, solving a simple quadratic equation. So the solution of an equation of the form x squared equals to c are going to be root c and negative root c. Okay, where does that come from? In other words, let's see what that means. So let's say, for example, note that if we had x squared minus, well, no, not minus, equals 4, we had this. Okay, so if I choose to move the 4 over, then I end up with x squared minus 4 equals 0. We can factor this out. That turns into x, well, okay, that's a difference of squares, so let me point that out. That's a difference of squares situation, so that'll be equal to x squared minus 2 squared equals 0. Difference of squares factors as x plus 2, x minus 2, which then equals to 0. And now we have the opportunity to use the zero product property. So we can separate this into two pieces. Either this equals to 0, or maybe this equals to 0. Good. So therefore, x equals to negative 2, right? We subtract 2 from both sides. Minus 2, minus 2. We add 2 to both sides. Plus 2, plus 2. And so this guy then becomes x equals to positive 2. So we have two possible answers. Either this one is true or this one is true. Okay, well, there was nothing special about the number 4. In fact, it could be any number that goes into here, as long as, well, I should say absolutely any number. If we have, say, for example, what if we had 3? X squared equals to 3. Okay, we'd still do the same process, move it over. We'd end up with x squared minus 3 equals to 0. And unlike 4, it's not going to result in something pretty like this one. But what we could do is kind of fudge it a little. We can rewrite it as x squared minus root 3 squared. Root 3, positive root 3, right? So this is the decimal such that when you square it, it equals to positive 3. So we can have that equals 0. And now we can use the difference of squares to separate this as x plus root 3, and then x minus root 3 equals 0. And now we can break this up into pieces. So either x plus root 3 equals to 0, or x minus root 3 equals 0. We can subtract this root 3 from both sides. And so we get that x equals to negative root 3. Or we can add root 3 plus root 3 equals to, well, plus root 3 plus root 3. So we end up with x equals to positive root 3. Okay, so for very simple cases where we have x squared equals to some positive constant, then we could do it this sort of longer way of moving it over, setting it to 0, using the difference of squares property to separate it as a product of two binomials, and then using the zero product property to separate it like this. But because this is a very common thing we run into math, somebody invented a little shortcut. And that little shortcut is to use this notation. Instead of all the work we just did, x squared equals to 4, someone thought, well, why don't we just say that this must mean that if we took the square of both sides, took the square of this side, took the square of that side, that these two operations would undo each other, therefore we'd end up with just an x, and then over here we would end up with a 2. But wait a minute, it's not just the 2, there's also the minus 2, right? There's 2 answers. Therefore, we just kind of memorize this. When you take the square root of both sides, you must introduce the plus and minus so that you can get both answers. Okay? All right, so that's what this is saying. If we have something simple like this, the solutions of this equation are x equals to root c and x equals to negative root c. Okay, so if we want to stay within the real numbers, of course, c is going to have to be 0 or greater, because if it isn't greater, if it's a negative number, then when we take the square root of both sides, we're going to end up with an imaginary number, and for the moment, we're still kind of ignoring it. We're going to get into that very soon. But for now, you'll see that I think everything we run into in this section is going to give you a positive number there, or 0 or greater, so that we don't have to run into the case where we're taking the even root of a negative number. Okay? So all this is saying is the same thing I just did up there, but just doing it in general. So if we have x squared equals to c, we can subtract c from both sides. We end up with x squared minus c equals to 0. We can do that same little trick I did above where we can rewrite this as root c squared equals 0. Therefore, that must mean that x plus root c times x minus root c, right? We can separate this by the difference of squares equals 0. And now, by the zero product property, we can separate this into x plus root c equals 0, or x minus root c equals 0. And so we can end up with x equals to negative root c and x equals to positive root c. Right? Okay, but this is the reason why it's true, but there's this cute little shortcut that we get to use. X squared equals to c. So what most people do is they take this root, take the square root of that side, take the square root of that side, introduce the plus or minus, and then these two operations cancel, so we end up with x equals to plus or minus root c. Right? So we end up with the same solutions. It's just that the reason why we have this plus or minus is a little mysterious to people. I don't know if it's clear to you guys, but hopefully it was. Maybe it is. Whatever. Hopefully it's clear now. And remember that this notation then means that there's two answers. There's the answer with the plus and there's the answer with the minus. This plus and minus is just the way of writing this in a shortcut sort of way. Right? These are equal to both of these answers. Okay, so here's a couple quick little examples. If I had x squared equals to 5, then just take the square root of this side, square root of that side. Don't forget to do the plus or minus. And so we end up with x equals to plus or minus root 5. Root 5 is an ugly decimal. It's not a perfect square. So you can take your calculator and turn it into a decimal approximation if you want, or you can just leave it alone. Right? So I'm perfectly okay with leaving it alone. So here's our answer. All right, what about in this case? Well, we do the same sort of thing. We just treat this as a little value, right? So, let w equal to x minus 4. So if we do that, we can do a little substitution here, which means that this is going to be w squared equals to 5. So we can move ahead with our process, take the square root of that, take the square root of that, put a plus or minus. And so we end up with w is equal to plus or minus root 5. And then we're not done yet because we weren't solving for w, we were solving for x. So we still have to come back over here now and plug that into there. So we end up with x minus 4. Put it in red. We end up with x minus 4 for the w is equal to plus or minus root 5. And now all we have to do is add 4 to both sides, plus 4 plus 4, and that gets us to our answer. X equals to positive 4 plus or minus root 5. So again, just to be clear, this means this is a shortcut notation to indicate two separate answers. One answer is going to be from the plus, so that'll be 4 plus root 5, whereas another answer is going to be to have 4 minus root 5. Okay, so let's see what the author did. So A was plus or minus root 5, and then B tells us that it's x minus 4 equals to plus or minus root 5, and there you go. So we get one solution is this one solution is that one. Right, so here's one solution for x, 4 plus root 5, and then another solution is x equals to 4 minus root 5. Okay, so if a quadratic equation is of the form a plus or minus x plus or minus a raised to the power of 2 equals c, then we can solve it by taking the square root of each side, right? So anytime something fits this form, then we can solve it this way. Another quick example would be x plus 3 raised to the power of 2 equals 9, for example. Again, we can eliminate this 2 here. We take the by taking the square root of both sides. X plus 3 squared equals to 9. So I'm going to take the square root of the left-hand side, That'll eliminate with that. And then I have to do plus or minus the square root of the right-hand side. So I'll end up with x plus 3 equals to plus or minus 3. And so finally, x, let's subtract 3 from both sides, minus 3, minus 3. We end up with x equals to negative 3 plus or minus 3. So we get two answers. X equals to negative 3 plus 3. That's otherwise known as 0. And we get another answer as x equals to minus 3 minus 3, which gives me x equals to negative 6. Okay, so let's go ahead and check these to make sure that they work. So let's check. We have blank plus 3 raised to the power of 2, and I want that to equal to 9. One of the answers is x equals to 0, and clearly that's true. 0 plus 3 gives you a 3 squared is 9. That's going to work out. Another answer is going to come in by this. So if we plug in a minus 6 into here, negative 6 plus 3 gives you negative 3. Negative 3 squared gives you positive 9. So both are valid solutions to this initial statement. Okay, so anything that fits this form, x plus or minus a constant squared equals a constant c, is going to be solved this way. Take the square root of both sides, don't forget the plus or minus, and then we just have to deal with that constant. That'll get us to our answer. Okay, but what if we had something similar but not quite the same? What if I had something like x squared plus 6x plus 5 plus 5. Okay, so what if I had something like this? Equals 0, and we wanted to solve. Okay, notice that this is different from the examples we had before. In the examples we had before, there was a binomial being squared, so we can take the square root of both sides, and that would eliminate the square on one side. But that is not the case here, so avoid this common mistake where people decide to take the square root of this side and the square root of that side, and somehow these guys cancel, and I'm not sure what they would do with the rest of it. But anyway, that's just bad math, right? We don't want that. Okay, so what do we want to do? Well, ideally, if this could factor nicely, we can also take advantage of the zero product rule, right? If we can rewrite this as a multiplication of two binomials. So chiefly, if we can fill in these blanks, x plus blank, 0, right? I want two numbers that multiply to 5, but add to 6. Okay, that'll work out. We got 5, and we have 1. That works out, right? That gives you 5. They multiply to 5, but they add up to 3. And then we can take advantage of the zero product property, which says that either the x plus the 1 equals to a 0, or the x plus a 5 equals to a 0. And so either x equals to negative 1 or x equals to negative 5 are both solutions. And we can check them. Check. We have blank squared plus 6 times blank plus 5 equals to 0. We can put a little negative 1 here and see if that's true. If we put a negative 1, we end up with we end up with 1 minus 6 plus 5 equals 0. And yep, that's true. So negative 1 definitely works. What about negative 5? Blank squared plus 6 times blank plus 5 equals 0. So this would be negative 5 minus 5. And so that'll be 25 minus 30. This would be 25 minus 30 plus 5 definitely equals to 0. Great. So we definitely have the answer. So if we can factor this nicely, that takes advantage of the zero product property, and then we can solve our equation this way. Okay, but we're gonna learn a slightly different way of doing a question like this, so that we get the exact same answers in a slightly different way, and it creates a new opportunity for sort of a new tool we can use with different equations. So what we want to do is do something called completing the square. Complete the square. In order to complete the square, consider the following. Consider what happens if I have x plus 3 squared. X plus 3 squared is x plus 3 times x plus 3, and then I FOIL this guy around. FOIL this guy, FOIL this guy, FOIL that guy. We know from our work in the previous section that that must mean that this is x squared plus 3x plus another 3x plus 9, which gives me x squared plus 6x plus 9. So x plus 3 squared equals x squared plus 6x plus 9. So if we compare it to the original question that we were working with, come back over here and think about that original question, it's very similar to that one. X squared plus 6x plus 5, that's very similar to x squared plus 6x plus 9. If this had been a 9, we would be able to easily factor it into this. Completing the square just means, well, why don't you just turn it into a 9, right? So here is what the process would look like. We start off with the original question given, x squared plus 6x plus 5 equals to 0. And then we go, well, okay, if there was a 9, if there was a 9 right there, things would work out so much nicer. So if you want a 9, why don't you just put a 9 in there? 6x, and we're going to just introduce a plus 9 in there. Now we can't just add a 9, that changes the value of our equation. So what we're going to do is also subtract 9. Add 9, subtract 9. Those two operations cancel each other. It's like we're adding 0. It doesn't really change the value of our equation, so we're allowed to do it. Okay, just make sure that you do both. You subtract the 9, you add the 9. Together they combine to give you a 0. Okay, so now we want to take the first 3, right? I'm not going to introduce parentheses or anything because that might change the signs, but if we just focus on the first 3 terms, that's a perfect square trinomial. It factors really nicely, right? In fact, it's right there. It's this one. It factors nicely. So now I can convert those first 3 values into x plus 3 squared. These two over here, well, we're just going to combine those two. I have a minus 9 and a plus 5. Together they combine to give me a minus 4. Minus 4 equals 0. And now all I have to do is move that minus 4 to the other side. So let's do a plus 4 plus 4. And so I'll end up with x squared space there. So I'll end up with x plus 3 squared minus equals to positive 4. And now that lets me solve for this, that easier method that we've learned. We can just take the square root of both sides. This side squared equals to 4. So I'm going to take the square root of this side. That'll cancel with that square. And then do plus or minus the square root of that side, which then gives me the x plus 3. X plus 3 equals to plus or minus root 4. That's going to be plus or minus 2. And then I can add, or I can subtract 3 from both sides. Minus 3, minus 3. And then that will end up with the 2 answers that I need. X, right, these guys cancel. X equals to minus 3 plus or minus 2. Right, that leads to x equals to negative 3 plus 2 as one of the answers, or x equals to negative 3 or x equals to negative 3 minus 2. So x equals to negative 1 is one of the answers, and x equals to negative 5 is the other answer. Same results we got from over here. Negative 1 and negative 5. We got the same answers over here. Negative 1, negative 5. Okay, but this procedure, this process of solving it is called completing the square. All right, let's take a look at some of the most popular perfect square binomials. So if we had x plus 1 squared and we FOILed it, we would end up with x squared. The middle term would be 2x plus 1. If we had x plus 2 squared and we FOILed it, we'd end up with x squared plus 4x plus 4. If we had x plus 3 squared equals to x squared plus 6x plus 9, we just worked with that one. If we had x plus 4 squared, we would end up with x squared plus 8x plus 16. And let's do one more. X plus 5 squared equals to x squared plus 10x plus 25. Okay, so now that we see nice little patterns for perfect square binomials, then if you were working with something like this, right? So let's say you were given the following equation to solve, right? Solve x squared plus 8x plus 5. So this one looks a lot like this one. X squared plus 8x, but instead of a 16, I have a 5. So I can use this, I can use my understanding of this to manipulate this one a little bit, right? And it could be equal to 0, it could be equal to 1, doesn't matter, let's say it's equal to 1. So I can manipulate it. I'm going to come back over here, I'm going to have my 8x, and then I'm going to introduce that special value, which in this case is going to be 16. Plus 16 minus 16, and then I'm going to put a plus 5 equals to 1. This is what's going to fix it, because now I get to have a perfect square trinomial for the first 3 terms. That's going to turn into x plus 4 squared, and then I get to combine these last two, combine these into minus 11. Minus 11 equals 1, and then I can move forward from there, right? I'm going to add 11 to both sides, take the square root of both sides. I think the solution is clear after that, right? This is the initial hard part. How do we factor this or semi-factor it, get it to a point where we can solve it, right? Let's try one more. Let's say we were given x squared plus 4x plus 3 equals 5. Okay, so then again, this one looks an awful lot like this one, right? And I know that it factors like that. So if I only had a plus 4 is what I'm thinking. X squared plus 4x, and then because we want that plus 4 there, just because I know my patterns of perfect squares, I would put a plus 4 there, a minus 4, add it, subtract it, add and subtract the perfect amount, and then leave everything else alone. Plus 3 equals to 5, and once again, we've achieved the magic. The first 3 terms are going to be a perfect square trinomial. They give me the x plus 2 squared, right? That's equal to this. And then we combine the last two, these last two then combine into giving me a minus 1. Minus 1 equals 5. And again, just like before, I think after this point, everything is fine. I can add 1 to both sides, and then I could just take the square root of both sides, and the answer should be clear after that. So this first step here, these first steps, this is the hard part. How do you take that original question and rewrite it into this? And, well, I kind of cheated a little bit here in that I wrote down some of the most basic, simple, perfect square binomials, and then I happened to provide a question that uses one of those. So you won't always be given that. The real tricky part is, how do we know to add a 16? How do we know to add a 4? If we're given some other random equation, like let's say I gave you x squared plus 26x plus, I don't know, 17 equals 8. If I give you this one, how do I know what to add and subtract, right? What's the perfect amount to add and subtract? Okay, so to figure that out, let's look at the pattern that exists between these values. So let's look at the first one we worked with, this one. Notice that we have an 8 there, and we have a 16. That's the thing we needed to add and subtract. The perfect amount was to add and subtract the 16. And then that led to this guy, right? X plus 4 squared. What's the relationship between all those? Notice that if I take the 8 and I do half the 8 squared is equal to 16. Right, so notice that, right? So my point being that when I was working with this guy here, I'm at this stage, and I'm like, how do I get this 16? How do I know that I need to add 16? Well, this is what I want to do. I want to take half the 8 and square it. That's the exact same rule that happens over here. Notice that, again, the relationship between this number and this number is, say, that it's half of this squared. And that's the same thing as this one, too. Half of 2 is a 1. 1 squared is 1. Half of the 6 is a 3. 3 squared is 9. Half of the 10 squared is 25. So that pattern exists all the way through. Okay? So again, if you're given this question right here, and you're like, okay, how do I solve this? I need to determine this. What's the perfect thing to add or subtract? And so the pattern, half the battle in math is to find interesting patterns. So the pattern is to look at this term, the constant in front of the x to the power of 1, half it, and then square it. Half this term squared is the perfect thing to add and subtract to make this whole thing work out. Right? So following all that in mind, keeping all that in mind, if I have this new question over here, and we want to figure out, okay, what's the perfect thing to add and subtract here? What's this little red part that I add and subtract? Well, we would focus on this number. We want to half that and square it. So we want to do half of 26 squared. Well, then that would be the same thing as 1/2 times 26 squared. In other words, 13 squared. 169. Okay, so armed with that, I can see that what I need to do is add and subtract 169, and that will lead to the perfect square trinomial I need to solve this. So I would copy it back down, x squared plus 26x, and then I'm going to add the perfect amount, which is going to be that 169 plus 169, and also subtract that amount. Whatever you add it, you subtract it, and therefore you haven't really changed anything. So add and subtract 169 plus 17 adds up equals to 8. So I've just copied this question here, and then I've inserted the perfect amount. And just like in all the other cases, that's going to result in me having a perfect square trinomial here. It's going to guarantee it. And then something else. Now, what's that perfect square trinomial going to be? Well, notice that in every single pattern, it's going to be the constant that goes here is exactly half of that one. Right? That's another pattern that we notice. This is exactly half of this one, and this one is exactly half of that one, and this one's exactly half of that one, right? So that's the pattern that exists with these very basic binomial squares. So it's half of this gets squared, gives you the thing you add and subtract. But when we actually factor it, it's really just half of that, right? Again, just following a pattern, half of that is what goes there. So keeping that in mind, I know that it's going to be half of this that goes in my binomial. You can always check it once you do it. Do a little guess and check and see if it works out. So that means that this is going to be a perfect square binomial, and it's going to be x plus 13 squared, right? Again, because this is exactly half of that, including the sign. It's positive, so I leave it as a positive. So half of that goes there. Half of that squared is the plus or minus that we do there. And then we just deal with whatever is left over. I have minus 169 plus 17, so that'll be minus 152. Minus 152 equals to 8. And then just like before, the rest is just going to come from, let's go ahead and finish this one out. It'll be plus 152 plus 152. Right? Add 152 to both sides. So I'll end up with x plus 13 squared is equal to 160. And now that I have it in this format, I know that the next thing I can do is just simply take the square root of both sides. Take the square root of that side, plus or minus the square root of that side. And, I don't know what that is, but it's some decimal. I can use my calculator to approximate it, or I can leave it alone. On the left-hand side, these two operations undo each other, and I'll just be left with x plus 13 equals to plus or minus root 160. And then finally, I just subtract 13, and I get that x equals to negative 13 plus or minus root 160. Right, so those are my two solutions to this equation. Right, so if the original equation was, let's check it. Let's go over here. So my original equation was this: solve x squared plus 26x plus 17 equals to 8. And I'm concluding that there are two solutions. One solution is x equals to negative 13 plus the square root of 160. And the other solution is going to be x equals to negative 13 minus root 160. Right? So two different solutions. I can check it. I can turn this into a decimal approximation. So let's do that. Okay, so square root of 160, that's going to be equal to 160 to the power of, and we know we can turn that into a little fraction, 1/2. 1 divided by 2. And that'll be the same thing as the square root of 160. So it looks like it's 12.6491164-ish. Okay, and so we'll have negative 13 minus that number is one value, and the other one is going to be negative 13 plus that value. So we got to get the 160 to the power of 0.5. That's another way we could do this. 1/2 is the same thing as 0.5, so we can get the same answer that way. And the other one was going to be negative 13 plus that answer. So from here we get that one answer is negative 25.6491. 6491. So negative 25.61, that's this one. And then the other one was 0.350, that's going to be a 9, that's going to be 01, 3501. So those are just a couple of decimal approximations to the answer, and we can check it, we can confirm that we're getting the right answer, or approximately the right answer, by plugging it into here. Blank squared, I'll make a little more space there, blank squared plus 26 times blank plus 17 equals to 8, and hopefully if things work out, it must be in that negative 0.3501 squared plus 26 times negative 0.3501 plus 17 is approximately equal to 8. So let's check it. So approximately negative 0.3501 to the power of 2 gives you that guy. And then plus, and then in parentheses, I'm going to put 26 times negative 0.3501, close parentheses, plus 17, and this should be pretty close to 8. Keep in mind, I did round. Okay, so the rounding is a real issue here. I think that's what it is. So if we wanted to be a little more precise, let's go back to, what was it? Negative 13 root. So root 160 to the power of 0.5 gave me that, and then plus negative 13. That was this thing. Okay, so let's be a little bit more precise and go out a few more decimal places. Let's go out to the 94. So 3508894. So this should be 8894. 8894 instead of that. 35.0 negative. Okay, so now let's try plugging that into here and see if it gets a little closer to the 7. See if we got rid of some of those errors. So I'm going to take this number and plug it into there and plug it into there, and hopefully I get my 8 a little closer, since the previous rounding gave me a really bad answer. Okay, so it's going to be negative 0.350889 close parentheses to the power of 2 plus, and then I'll put it in parentheses, 26 times, and then it's going to be negative 0.35088894 close parentheses plus 17. So it should be a little closer to 8 now. Much closer to 8. So see, rounding has a pretty big impact. Okay, but we got that right answer, and then we can also check the other one. Let's see how the rounding affected that one. Let's try that one. So we could plug in negative, coming back over here, so let's plug in the other possible solution, negative 0, no, not negative 0, negative 25.6491. Again, we're going to put it right in there, and see if we have the right answer. Okay, so we have negative 25.6491, and want to raise that to the power of 2. So that gets squared, plus parentheses 26 times negative 25.6491 plus 17, and again, hopefully we're pretty close to 8. Whoa, not close to 8 at all. 25, 26, 26, 25. Okay. This is where I made a mistake. I forgot to wrap this in parentheses, so when I squared this, it gave me a negative answer. Right? It's pretend I did that on purpose as a teaching moment. Let's see, negative 25.6491 in parentheses raised to the power of 2. And then plus, in parentheses, 26 times negative 25.6491, close parentheses, plus 17. Enter, and again, very close to 8. So definitely we've confirmed that we have our two solutions. Okay, so we've established that this is one solution to our equation, and this is another solution to the equation. Okay, quick little recap. How did we do this? We needed to insert the perfect amount, right? That's what the completing the square process is all about. Inserting the perfect amount, adding and subtracting the perfect value that will result in a perfect square trinomial for the first 3 terms, and then some other constant you can deal with. The pattern that we're going to notice is that the perfect thing to add is going to be half this constant, right? This constant, we half it, so we multiply by half, square it, and that's the perfect thing that'll work. Notice that so far in every single example we've been working with, there happens to be a perfect little 1x squared there, plus a constant x. If we work with something a little more complicated, like some constant other than a 1 there, then we'd have to do one other little thing. So we'll get to examples like that in a little bit. But as long as we have a nice pattern of x squared there and some constant x there, then the pattern of completing the square is always the same. Half of this squared is the perfect thing to add and subtract. That creates this perfect square trinomial. And then that will result in this binomial where this constant is exactly half of that one. Right? This is all based on patterns. I haven't done any theorems or anything to prove it to you. It's just a pattern that emerges and works out well. Okay? Once we get it to this stage, hopefully everything else is pretty easy. It's just this initial part here that's a little bit difficult. Okay, so the pattern in general is going to be this. So given some equation of the form x squared plus bx plus c equals 0, given something of this form, then I want to complete the square by adding or subtracting the perfect thing. So what we want to do is insert the perfect thing here. We want to add and subtract one half times the b squared. That's going to be the perfect thing to add and subtract. Well, that's just going to be b squared over 4. And now coming back over here, this is going to be x squared plus bx. And then we add and subtract this plus b squared over 4 minus a b squared over 4 plus a c equals 0. Okay, so then that means that these guys right here are going to be a perfect square trinomial guaranteed by this process, and in fact it's going to be x plus half of that. That'll be b over 2 squared, right? That's the pattern that always happens. That guy right there, it's half of that squared, and then we're left with this other stuff, right? These are just numbers. B squared over 4, it'll be some constant, some number. So it'll be a minus b squared over 4 plus c, whatever that is. And then we can just move that to the other side, take the square root of both sides, don't forget about the plus or minus, and then we'll be on our way to solving our answer, right? So what I really just wanted to point out was this initial part here. Okay, so the rule for this is that to make x squared plus bx a perfect square, we're going to add b over 2 squared, the square of half the coefficient of x. This gives the perfect square x squared plus bx plus b over 2 parentheses squared, and then that'll be a perfect square trinomial, which gives you this in its factored form. All right, let's try this process one more time. Let's say we wanted to solve this. Again, the first thing you would do is try and factor it nicely. Are there two numbers that multiply to 13 but add to -8? I think pretty quickly you realize that that's not going to work out very well. Okay, so then we need to try complete the square. Right? Complete the square. Right? So what we want to do is we want to add and subtract the perfect thing. And so looking at my patterns, I have -8x. What I want to introduce is to add half of this. Oh, here, let's just finish it. Plus 13 equals to 0. So I want to take this number there, including its sign. I want to half it. So we want to add and subtract. Add and subtract. Add and subtract the perfect thing, which is going to be -8. We multiply it times half to half it, and then square it. That's going to be -4 squared, which gives you +16. +16 is going to be that perfect number that we add and subtract. So we take x squared minus 8x, and then we're going to squeeze in a +16, also subtract a -16, add and subtract it so that we don't really change the value of our equation, and then everything else stays the same. We still have a +13 equals 0. Good. This process guarantees that the first three terms are going to be a perfect square trinomial, and there's a nice little pattern to that. It's going to be of the form x plus half of that, -8 over 2 squared. Right? That's always the pattern. It's half of this is what belongs there. Half of this squared is what we add and subtract. Then we just have to deal with the remainders. We have -16 plus 13. They combine to give me -3. -3 equals to 0. Now I can simplify this a little bit. This becomes x minus 4 squared minus 3 equals 0. Now I can move this to the other side. +3 plus 3. And I'm going to take this guy up here. That must mean that x minus 4 squared is equal to +3. Okay, these guys cancel. And now I can take the square root of both sides. Squared equals to 3. So square root this side plus or minus the square root of that side. I end up with x minus 4 equals to plus or minus √3. Again, I can use my calculator to approximate it as a decimal, or I can just leave it alone like this. And finally, I add 4 to both sides. So +4 plus 4, and I end up with x equals to 4 plus or minus √3. Right, so this is again a shortcut for two possible answers. X equals to 4 plus √3 is one answer, and the other answer is x equals to 4 minus √3. Good. So we can turn that into decimals. Let's look at our calculator and figure out those decimals. We have square root of 3 is equal to that decimal. So we have 4 plus that, that's going to be 5. So that'll be 5.732051. So that's adding 4 to this 1.73. That's how we get this one. And then 4 minus that previous answer. 4 minus that gives me this 2.267949. 267949. So we get this answer, we get that answer, We have two possible answers. Now all we have to do is plug it into our equation and confirm if it's in fact if they're both in fact valid solutions. Right? So let's just check it. Let's go back up here. Let's check. The original question was x squared minus 8 times something plus 13 equals to 0. So all we have to do is replace the x with this quantity in there and then this quantity in there and check and see if that's in fact the case. 5.732051 and 5.732051. Is it true that this gives me a true statement? So let's check with our calculator. Clear. Okay, so parentheses 5.732051 close parentheses to the power of 2 and then minus 8 times 5.73251 close parentheses plus 13, enter, and we get something really close to 0, right? So again, I did some rounding, and that's why it's not going to be exactly equal to 0, but this is a really small number, right? Because we have times 10 to the negative 7. So that means we know that there's going to move this decimal over to the left 7 spaces. That means I'm going to introduce 6 zeros. So I'm getting from this, what I'm getting is, from all of this, what I'm getting is 0.12345 zeros and then a bunch of 6s. So pretty small, pretty close to 0. Good. And then if we try the other one, we plug in this decimal into there and this decimal into there, we'll be able to check to see if this is a valid answer. So parentheses 2.26794 close parentheses to the power of 2 minus 8 times 2.26794 close parentheses plus 13. Okay, so again, close to 0, yeah, the exact same answer. So very, very close to 0, just off by a little bit because of the rounding issues, but pretty clearly the right answers. Okay, so this is the process of completing the square. We gotta note that we have something that fits the form, and the form is going to be the variable squared plus or minus a constant times the variable plus or minus a constant equals another constant. As long as we have something that fits that exact form, then we can always add and subtract the perfect amount in order to complete the square, in order to make the first 3 terms a nice perfect square trinomial. So we always follow that same pattern. It's going to be whatever that constant is right in front there, we're going to half it and square it. That'll be the thing we add and subtract. And then we're going to create this perfect square trinomial for the first 3, terms. And it'll follow this pattern. It'll be x plus whatever this term was, whatever this was, we half it, and that's what belongs right in there. Okay, so here's what the author did, same thing. Okay, so they moved the 13 first, and then they added 16 to both sides. Adding 16 to both sides is the same thing as adding and subtracting 16 to just one side, right? So hopefully that's clear. I think that kind of confuses people sometimes. So I can either add 16 to both sides, or I can choose to do this, what I've been saying so far, add 16 and also subtract 16 from just one side. If you add and subtract it from just one side of the equal sign, then you haven't really changed anything. So you don't have to do anything to the other side. We've added a different form of 0. But adding and subtracting 16 to just one side is the same thing as adding 16 to both sides. So they both work out to be the same thing, right? And we knew it was 16 because of the pattern, right? There's this pattern that exists, and we know that the perfect thing to add and subtract is going to be this guy divided by 2, or half that squared, right? That's what this is pointing out. The complete the square process indicates that the perfect thing to add and subtract is half of the 8 squared. Good. And then once we have that perfect square trinomial, again, the pattern is going to be that we get this little binomial here where it's x plus half of that squared in parentheses. After that, everything else should be pretty straightforward. Okay. Well, what if we don't have a perfect question like before where we have this 1? What if we have a 3 out in front? How do we deal with that? Well, the pattern only works as long as there's a 1 there. That pattern of adding half of this squared and all that, that pattern only works as long as we have a 1 there. Because all of it is reliant on simple binomial squares, right? Coming up here where I did all these simple ones. Come back up here. Well, these guys here. Remember this little pattern? Notice that in every single case, I have this very easy 1 in front. 1 times all that, 1 times all that, 1 times that, 1 times that, 1 times that. And that is the result of these really straightforward binomials that are being squared. And all of the binomials have a 1 in front of the x as well, making them easy. A 1 there, a 1 there, a 1 there. The minute I think about something more complicated, like 2x plus 3 squared, then it gets a little more complicated and the pattern is not going to work out so nicely. It's no longer going to be the case that this one is always half of that, the way it is here. It's always half, it's always half. And it's no longer going to be the case that this constant out here is always this one squared, this one squared, this one squared, right? So it's important to make sure that we have a 1 there because it stems from this very simple pattern that happens when we square binomials that happen to have a very simple pattern like this one. So what do we do when we have something that's not a 1 there? How do we deal with it then? The way we deal with this one is going to be to simply factor out the 3. Right, so let me put this over here. So what we're going to do is step 1, we're going to factor out a 3 in order to guarantee that there's a 1 there. So we're going to factor out a 3, and then we end up with x squared minus 4x. Now this last constant, it might factor out nicely. It just so happens in this case that 3 is a divisor of that term, and that term. But in fact, it doesn't have to be a divisor of the last one. Many of the questions you'll face in homework only have a common divisor for the first 2, and they might not have a common divisor. You might have to fudge it a little bit and do a little bit of algebraic trickery, which I'll show you in a little bit, if they don't have a common divisor. Okay, so I'm just going to focus on the first 2 terms. I can factor out a 3 from the first 2 terms, and then I have this plus 6 over here equals 0. And now what I'm going to do is I'm going to focus just on this part in here. This part in here fits the pattern exactly the way I want it. It has a 1 out in front, plus or minus some constant x, and so I can add and subtract the perfect thing inside these parentheses and get a perfect square trinomial in there. Okay, so following my pattern, I know that I need to focus on this. Remember, the perfect thing to add and subtract is going to be equal to half this squared. So add and subtract this, which is 1/2 of the negative 4 squared, which is going to be equal to negative 2 squared, which equals to positive 4. So adding and subtracting 4 is the perfect value that I can introduce in order to guarantee a perfect square trinomial inside the parentheses. Again, notice that I have a 1 now after I factored out that 3. So I'm going to leave my 3 out here. I'll have an x squared minus a 4x. And now what I'm going to do is I'm going to introduce a plus 4 and at the same time subtract minus 4. Adding and subtracting it gives me a plus 0. So I haven't really changed anything. Plus 6 equals 0. Right? So the only thing I did was introduce a plus minus 4 in here. Good. And then the process of completing the square, we got to rely on it. It tells me that that's going to work out perfectly. That's a perfect square trinomial. And the pattern is that it'll be equal to x plus half of that guy. I'll just put it. Half of that guy is equal to negative 4 divided by 2. Half divided by 2 squared. Right? It's the quantity, it's this thing before we squared it. That's what belongs in here. We still have this minus 4. All of that is still inside these giant parentheses. There's still a 3 being multiplied by all that, and there's still a 6 equals to 0. Good. Okay, so next we're going to distribute this 3. This 3 applies there, and then this 3 also applies there. So go ahead and distribute that guy. I'll end up with a 3 parentheses x, and now this simplifies to just give me minus 2, right? 1/2 times negative 4. This is just going to be minus 2. So minus 2 squared minus 12, and that takes care of these outer parentheses, right? This parenthesis and this parenthesis are the same as this parenthesis and that parenthesis. So once I distributed this 3, I got rid of those parentheses. I still have a plus 6 out here. Plus 6 equals 0. And now I can combine these guys, combine these two to give me a minus 6. So I get 3 parentheses x minus 2 squared minus 6 equals 0. And now things are looking better. I'm going to add 6 to both sides. Plus 6 plus 6. These will cancel. And that's fine. So let's go over here. So I'll be left with 3x minus 2 squared equals to positive 6. I'm going to divide both sides by 3. Divided by 3, divided by 3. It'll cancel on the left-hand side. I'll be left with an x minus 2 parentheses squared equals to 2. And then we can use our shortcut, right? We can take the square root of both sides. Minus 2 squared equals to 2. Which means that I can take the square root of this side plus or minus the square root of that side. Almost there. We end up with x minus 2 equals to plus or minus root 2. Again, we can use our calculator to get approximation, but we can just leave it like that. And now we add 2 to both sides, and that leads us to our final answer. X equals to 2 plus or minus root 2. Right, so that's 2 answers. One of them with the plus 2, 2 plus root 2, and the other answer is going to be 2 minus root 2. Okay, so that's the process of completing the square. See what the author did. The author moved the 6 over to the other side first, factored out the 3. Then we added 4 to both sides, found that perfect square trinomial, was able to break that down into there. Okay, so we got the same answer. Maybe went about it in a slightly different way, but very, very similar. So we can use this technique of completing the square to derive a formula for the roots of a generic quadratic one. Okay, so let's solve this in general, is what we want to do. So let's say that we have ax squared plus bx plus c equals to 0, and this is where, there's so many letters running around, it's easy to get lost. The a, the b, and the c are just constants, and a is not equal to 0. This is for a, b, and c equal to constants, and also a is not allowed to be equal to 0. If a was 0, then this whole thing would just simplify to something much easier, so we're just ignoring the possibility that it could be 0, right? Otherwise, it's just too easy. Okay, so this is saying, for instance, this could be a 3x squared plus 2x plus 7 equals 0, right? This would be an example of this polynomial where the a is a 3, the b is a 2, and the c is a 7. That's just one example. Another example could be one where the a is a -5, the b is a 3/4, right? Nobody said it has to be a whole number. It could be any constant. And then we have a plus, and maybe it's a -3. Right? Could be a negative, could be a fraction, anything at all. They're just constants. But it's important to note that even though there's a lot of variables running around up here, a, b, and c are constants, and the variable we're working with is really just the letter x. Okay, so how do we complete the square? Complete the square process on this x squared plus bx plus c equals to 0? Well, we're going to follow the same pattern we just followed up above. Right? Look what we did. The first thing we do is to guarantee that there's a 1 here by factoring out the 3, factoring out the constant in front of the x squared from the first two terms. So that's the first thing we're going to do. And let's do that over here. First thing we're going to do is factor out the constant a. So I want to be able to rewrite this as a times, well, x squared is easy. Now this one's harder. How do we factor out an a from a b? Well, it's a little trick. What we want to do is rewrite this as a fraction, b over a, x, parentheses. Note that if I distributed this, a times x squared is ax squared. A times b over a, the a's would cancel, giving you just the b. And now I'll leave the plus c alone, leave it like that. And now I have something that works out well. I have something with a 1 there. Good. So now I can complete the square on this part inside the parentheses. So what I want to do now is add and subtract the perfect thing. Add and subtract. And remember that the pattern has always been to do half of this quantity squared. So add and subtract 1/2 times b over a, and then all of that gets squared. That's going to be the perfect thing to add and subtract. So that's going to be equal to b squared over 4a squared. That's the perfect thing to add and subtract to guarantee that this is perfect square trinomial. So I'll have a times x squared plus b over ax, and now I'm going to add the perfect thing. That perfect thing is this b squared over 4a squared, and at the same time I have to subtract it, b squared over 4a squared, close the parentheses. I haven't really changed my equation because I'm adding and subtracting the same amount, so I can just put a plus c equals to 0, and I'm good to go. So this step is equivalent to what we just did right above. We're just mimicking this process right here. The first thing I did was to guarantee that there's a 1 in front here by factoring out a 3 from the first two terms. Once I have that, then I did complete the square on just this part inside the parentheses by adding and subtracting the perfect thing. And the pattern is to do half half of this, it's right there, half of that squared. That gives me the perfect thing to add and subtract. So when I had numbers there, I could actually calculate it and simplify it. But with all variables, a, b, c, this is where I ended up with the b squared over 4a squared. And that's where we add and subtract. So I'm really at this stage. Next, what we want to do is combine the first three terms. And the pattern indicates the first three terms are going to be a perfect square trinomial of the form parentheses x plus blank squared, where that blank is half of that guy. That guy half is this. Another way to look at it is this thing before you squared it. That's what goes right in there. So that's the way the pattern works. So we're going to have to rely on that pattern down here. So now, simply relying on that pattern, I know that it must be true that the first three terms are going to be a perfect square trinomial and that they will fit this pattern, x plus blank squared, and the blank in there is going to be half of this. So it'll be equal to b over 2a. That's what goes in there, b over 2a. Okay, and then I still have this other larger parenthesis, and I still have this minus b squared over 4a squared. I still have this a out here, which multiplies across all of this, plus a c equals to 0. The next thing I want to do is to get rid of these parentheses, right? So I have these parentheses here. It's a times all of that. So a times all of this, and to get rid of those parentheses, I'm going to have to distribute this a. So it'll be a times this quantity, and then a times that quantity. So I'm going to go ahead and distribute it, and I'll get a parentheses x plus b over 2a squared minus a times b squared over 4a squared plus c equals to 0. All right, this a then reduces with that guy right there, and we'll end up with b squared over 4a, only one of those a's, so one of those a's cancels. This a I do not want to introduce into there because this is getting squared. I can't do that. The only way you can combine them is if it's also squared, but we don't want to do that. Instead, remember, our goal is to solve for x. There's only one unknown variable here, x. Everything else is just constants. Up in the example above, we were dealing with numbers, so this was a number, this was a number, this was a number. So what we did was to push everything to the other side, combine these guys, push them to the other side, and then divide by the a, take the square root, and that gets closer to our answer. Okay, so next I want to move this fraction to the other side and move this constant to the other side. And I'm using this language of move it, right? But really I want to cancel it by adding or subtracting the perfect value. So let's make a little space here. So this is going to be equal to a parentheses x plus b over 2a squared minus b squared over 4a plus c equals 0, and this is then going to be equal to a x plus b over 2a squared is equal to, and then that will mean that this fraction is going to be positive on the other side, right? Because this little notation here, this one means that this is a subtraction. So therefore, I'm going to add this fraction to the other side. So I'll get a positive b squared over 4a. And now I have a plus c. So if I move it to the other side, I'm going to have to cancel it on this side. So I'm going to subtract c from both sides. So I'll add a minus c. Okay, let me zoom out a little bit. Okay, so now let's copy this guy over here. So I have a parentheses x plus b over 2a parentheses squared is equal to b squared all over 4a minus c. So I want to combine those two. I need a common denominator. So I'm going to put a little 1 underneath here. And then I want to multiply it by 4a over 4a. So I'll end up with a parentheses x plus b over 2a squared is equal to b squared over 4a minus 4ac all over 4a. Now they have the same denominator, so I can bring them together. I'll have a parentheses x plus b over 2a squared is equal to b squared minus 4ac all over 4a. I'm going to multiply both sides of the equal sign by 1 over a. On the left-hand side, that cancels with that. On the right-hand side, I can multiply by 1 over a. And so I'll end up with x plus b over 2a squared equals to b squared minus 4ac. And I think it's starting to look a little familiar. 4a squared. Next, I'm going to take the square root of both sides. So take the square root of this side, and then plus or minus the square root of this side. On the left-hand side, the square and the root will cancel out. I'll end up with just x plus b over 2a equals to plus or minus this giant root, which I can separate into a giant fraction where I have the root of the numerator and then the root of the denominator. The root of the numerator is going to be this b squared minus 4ac, and the root of the denominator is going to be this 4a squared, which then is just going to simplify to 2a. Good, so let's copy that. This is x plus or minus b over 2a is equal to plus or minus the square root of b squared minus 4ac all over 2a. Now I move this, oops, why is there a plus or minus? It's just a minus. I'm just bringing this down, that should be a plus, not a plus or minus. Okay, so now I'm going to subtract that from both sides, and we end up with x equals to minus b over 2a plus or minus this whole fraction, which is going to be b squared minus 4ac all over the square root of that whole thing, all over 2a. And then these two have the same denominator, so we can combine them into one big happy fraction, and I think most people begin to recognize it now. This is going to be x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so kind of squeezing it in the bottom there. Hopefully it looks nice and familiar. So I'm going to squeeze it all in one big window here, but we'll see a nice, I'll copy it down and zoom into it in a little bit. So what did we do? We started out with something that fits this form, a quadratic that fits this form where the a, the b, and the c are constants, and also the a is definitely not 0. And then we followed the pattern we already established before, so we can complete the square on this process. Factored out the a, got that guy, introduced the perfect amount. Following the pattern, it's going to be this amount times 2 squared. That's how we get these guys.
The first three terms are perfect square trinomials. We can get to factor them this way, again, following our pattern. It's going to be of the form x plus this term times a half. That's how we get this guy. Then squared minus, from this guy, we get this. Distribute the a, and then simplify and solve for x. So after a little bit of algebra, we end up with this formula. So what we get is a general form for solving the value of x that solves these quadratic equations. Okay, so that's the derivation. Let's put it in a nicer box. So over here. So what we just came up with is this guy. It's called the quadratic formula. Let's go back to this. So it's the quadratic formula, and so it says that the roots of a quadratic formula of the form ax squared plus bx plus c equals to 0, where a does not equal to 0, are this. In other words, this is the solution, right? If we solve this, we'll get to figure out the values that make this a true statement without having to go through the whole complete the square process. So we solved it in general one time, and this is the formula we can derive from it. So we can use it to solve quadratic equations that fit this form, right? By using the quadratic formula, if you're allowed to. Half the teachers out there will allow it. Maybe half of them will say, nope, you're going to have to do it from scratch. I like both. So there will be cases where I say, you're not allowed to use a quadratic formula, figure it out. So you're going to have to do it the long way. And there'll be cases where I say, just use the quadratic formula or any method you'd like to solve it, since, of course, there's going to be other methods to solve these kinds of questions, namely the graphical method. Okay, so quick examples. Let's say that we're asked to solve this guy. This fits that form, right? This is of the form. This is of the form ax squared plus bx plus c equals to 0. That's where the a, the role of a, is being played by a 3. The role of b is being played by a -5. The role of c is being played by a -1. So we could do complete the square on this process, and then that will lead to the correct answer. But we've already solved this in general for any value of a, b, and c, and we have a formula, and that's what this is. So we could just apply our formula and get our result. So the solutions to this, are x equals to -b plus or minus square root of b squared minus 4ac all over 2a. And all we have to do is plug and chug here, just plug in the values. A is equal to 3. Right, so a equals 3 from there. B equals -5. Be careful with the signs. And C equals -1. So all we have to do is plug them into here. So x equals to negative blank plus or minus the square root of something squared minus 4 times something all over 2 times something. And so the b was a -5. Now be careful that the formula has its own sign. Right? The formula comes with a negative b there, negative. But then in this case, the b has its own sign of negative, so it'll be a negative times a negative situation. So -5 there, and then -5 in here. The a is a 3, so we end up with a 3 there and a 3 there. And then the c is a -1, so we put a -1 in there. Okay, so we just simplify that, and we end up with +5 plus or minus, zoom this up a little bit, +5 plus or minus the square root of 25 minus, so we end up with -12 minus -12, so it's going to be +12 all over 6. So then we just simplify this. We get 5 plus or minus root 37 over 6. So those are our two answers. We can leave it like this, or we can separate it into the two answers this way. We can say that one solution is x equals to 5 plus root 37 over 6. And another answer is x equals to 5 minus root 37 over 6. Five plus or minus root 37 over 6 is what the author did. And then you can just convert that into some decimal approximations. Looks like this is what we get, this one or this one. And we can check it by going back to our original equation, replacing the x by this decimal, and confirming that we in fact get a true statement, or close to it since this is a rounding. Okay, let's try one more. What about this one? Again, we could do complete the square on this process to find the x, but we've already solved it in general. So the quadratic formula tells me that this fits the form ax squared plus bx plus c equals to 0. This is where a is being played by a 4, and b is being played by a 12, and c is being played by a 9. So given that I have those values, then I know that the solution is going to be x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals to negative something plus or minus the square root of something squared minus 4 times something all over 2 times something. So b is 12. Let's put a 12 there and a 12 there. And a is a 4, so a 4 goes there and a 4 goes there. And c is a 9, so a 9 goes there. Okay, so we get that x equals to negative 12 plus or minus the square root of 144 minus 16 times 9 is 144. All over 8. So 144 minus 144, this just becomes 0. So we end up with x equals to negative 12 plus or minus the square root of 0, which is just going to be 0, all over 8. So x equals negative 12 plus or minus 0 is just going to be 0 over 8, or just x equals negative 3 over 2. Okay, so when the value of when the argument of this root function, what goes inside the root here, when it equals to 0, we end up with the square root of 0, which is 0. And then we no longer have two separate cases. This would be the situation where we only have one solution. It's just x equals to 3 over 2. Okay, so that's what the author did. Plug in those values, and that's how we get that. And then finally, how about this one? Again, this fits that form. Fits the form ax squared plus bx plus c equals 0. Right? Note that it equals to 0 every time, where the a equals to 1, the b equals to 2, and the c equals to 2 as well. Okay, so we just plug them into our formula. X equals our quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals negative b, negative 1 times something, plus or minus the square root of something squared, minus 4 times something else, and then 2 times something. So the a is a 1. That's going to be right here. This is a 1. This is a 1. The b is a 2. That's a 2 there. That's a 2 there. And the c is a 2. So this will be x equals negative 2 plus or minus, this will be the square root of 4 minus 8 all over 2. And so this is going to be x equals negative 2 plus or minus root negative 4 all over 2. Okay, so that means that we have a negative inside here. That means that we're going to get an imaginary solution, right? That's what this means, imaginary. Oh, okay, good. So, how do we deal with this guy? Well, we got to deal with the fact that this is a minus 1. So I know that we haven't quite covered that in this class yet, but it is a review class, so hopefully it looks familiar. What we need to do is deal with that minus first. So I'm going to pull out that minus and turn this into I, imaginary, root 4 over 2. If that, hopefully that looks nice and familiar and you can work with that. If not, then stay tuned. I think the next section covers imaginary numbers. Okay, so then we have minus 2 plus or minus I, and then the square root of 4 is a 2, so I'll just put a 2 there, all over 2. And so now we can separate this into x equals to negative 2 over 2 plus or minus I, and then 2 over 2. And so these guys reduce to just give you a 1, and these guys reduce to give you a minus 1. So we end up with x equals to minus 1 plus or minus I. Good. So again, that's just two solutions, one of them with the plus, one of them with the minus. So one solution is going to be that x equals negative 1 plus I, while another solution is that x equals negative 1 minus I. Right, so two solutions. Again, we'll talk more about imaginaries in the next section. I think that that's what the author did here. Oh, I guess, okay, they kind of, the author stopped there again. We haven't really talked too much about imaginaries. Maybe that's what we're heading into. Since the square of a real number is non-negative, the square root of negative 1 is defined as is undefined in the real number system. The equation has no real solution. So that's why we head into the imaginary numbers, which is in the next section. But I think for now, they just want you to stop here since we haven't talked about imaginary numbers yet. So jump the gun a little bit there. Okay, the discriminant is the argument of the root function, the part inside the root function. Notice in our equation, here it is. Notice that in our quadratic equation, we have this part inside here is equal to this b squared minus 4ac. That part of the formula is what determines what goes inside the square root. If that part inside there is 0 or larger, then this square root is going to result in, not 0, it's strictly greater than 0. Then this part here is going to result in a valid root. And so we'll end up with a plus or minus. We'll end up with two possible answers. If whatever is inside here equals to exactly 0, then this root is 0, and then we end up with exactly one solution. And if this part here, this discriminant, is negative, then we'll have a square root of a negative number, which means that we'll have an imaginary, so we'll end up with two imaginary solutions, right? No real solutions. And so that's what this is indicating for us. So let me combine that. So if we have b squared minus 4ac, if this part is exactly equal to 0, then we'll have negative b plus or minus the square root of 0 all over 2a. And so this part disappears and I'll only have one answer, negative b over 2a, right? Only one solution. That's this part over here. If the discriminant, this part inside here, is equal to 0, then the equation has exactly one real solution. That's that one. On the other hand, if this b squared minus 4ac equals some constant that's bigger than 0, some constant, maybe it equals to 3, or maybe it equals to 13, or some other constant, then this part will end up with negative b squared minus this part ends up being negative b plus or minus the square root of. So if the part inside here is some positive number, then this will be a valid answer. This will be some valid root. It could be a whole number, like if it was the square root of 16, then this would be 4. But if it was 13, then we would just leave it alone as the square root of 13. And then all of that gets still divided by 2a. This will result in two real number solutions. Okay? So either this part in here could be 0, or it could be a positive. And then, again, if the part inside the root, this discriminant, is negative, if b squared minus 4ac is negative, strictly less than 0, then when we apply this formula, we're going to end up with the square root of a negative number. We'll end up with negative b plus or minus the square root of a negative number, negative, divided by 2a. And this will result in imaginary solutions. So no real answers. That's what this means right here. No real solutions. No real solutions. Imaginary. So we'll look at those in more detail in the next section. But in some situations, you might not necessarily want an answer. You don't want to know what the solution x is. Maybe you just want to stare at it and determine real quickly whether this is going to have solutions, yes or no. Is it going to have one answer? Is it going to have two real answers? Is it going to have no real answers, only imaginary ones? And so a really quick way to do that is just to figure out this discriminant. Figure out what's the value of this part of the formula, the one that goes inside the root. And so some of your homework questions are just going to ask you to do that. Figure out the discriminant. So given these equations right here, use the discriminant to determine how many real solutions we're going to have. Okay, so all you have to do is figure out what this is. B squared minus 4ac. So for part A, for example, the discriminant is going to be 4 squared. That's the B. Here, let me label them. The A is going to be a 1. The B is equal to a 4. And the C equals negative 1. So we end up with 4 squared minus 4 times A times C times A times C, B squared minus 4AC, which gives me 16 minus is going to be plus 4. I end up with 20, and because 20 is greater than 0, I know I get two real solutions. Two real solutions. Good. For part B, let's label those. The role of A is played by a 4, the B is being played by a negative 12, and the C is being played by a 9. So now when I plug it in to figure out the discriminant, I'll get negative 12 squared, does this question be? Negative 12 squared, that's the b squared, minus 4a, which is 4, and c, which is 9. Oh, and we already worked with this one. This is going to be 144 minus 4 times 4 is 16. 16 times 9 is 144. So we get a 0. So there's going to be one real solution. One real solution. And finally, for C, left the best for last here, this one has the role of A is being played by a 1/3. The role of B is being played by a -2, and the role of C is being played by a 4. So now, applying it to my formula, b squared is going to be -2 squared, -2 squared, minus 4 times a is equal to 1/3 times c, which is equal to 4 times 4. Okay, so this is going to be equal to positive 4 minus 4 times 4 is 16/3. 16/3. And as a mixed number, I know that this goes into 16. 4 minus 5 and 1/3 as a mixed number. So I know this is going to be negative, right? I don't even have to worry about common denominators and all that. I know it's going to be negative. Or you can just turn it into a fraction by putting a 1 here, 3/3. We get 12/3. I know that this is also going to be equal to -4/3. Put that in here. A little 1 here. 3/3 is going to be 12. 12 minus 16 is going to be -4. So it's going to be -4/3. It's negative. So if the discriminant is negative, that means that I'm only going to have imaginary solutions. Therefore, there's no real solutions. No real solutions. Okay, remember, we're not trying to find the answer. We're just trying to establish if there are any solutions. That's what they want you to do here. Okay, and that's what we did here. The first one resulted in a positive number. Therefore, there are 2 distinct real solutions. The other one resulted in a 0. There's exactly 1 solution. And the last one resulted in a negative number inside the discriminant, inside the argument of the root function. So we end up with no real solutions. Okay, so let's cover a few other variations. Let's say that we wanted to solve this equation. Okay, so what we want to do with something like this is to start off by factoring everything. And the only thing that really needs to be factored is this guy. So I'm just going to rewrite the whole thing. 3/x minus 2/x minus 3 equals -12. And the way it factors is we have x squared minus 9. That's x squared minus 3 squared. And so we have a difference of squares. So this factors as x plus 3 times x minus 3. Okay, so that's going to become x plus 3x minus 3. What we want to do is find the LCD of all the denominators, and that's going to be as follows. LCD, the least common denominator. Well, there's a copy of x, there's a copy of x minus 3, and also a copy of x plus 3. And so using one of each of those, we'll be able to get the least common denominator. Okay, so I'm going to copy it here. 3/x minus 2/x minus 3 equals to -12 divided by x plus 3 x minus 3. And now I'm going to multiply this side by x times x minus 3 times x plus 3. I'm going to multiply this side by the exact same amount. X times x minus 3 times x plus 3. As long as I'm doing the same thing to both sides, I've maintained that equality. So I have to multiply all of it, right? I multiplied everything on the right-hand side by this amount, so I have to multiply everything on the left-hand side by the same amount. So I have to distribute. I'll end up with x times x minus 3 times x plus 3 times 3 over x minus, and then another, once I distribute, I get x minus 3, x plus 3 times, and I'll get a 2 over x minus 3 equals the right-hand side, which is negative 12 over x plus 3, x minus 3 times this, which is x minus 3, x plus 3. Good, so now a bunch of stuff will reduce. This x reduces with that one, and then this one reduces with that one, and then both of these cancel with both of those. So after all that cancellation, what remains is this product times a 3, so I'll get a 3 times x minus 3 times x plus 3, and then minus x times x plus 3 times 2 equals to negative 12 times x. Okay, so we're going to have to do a little bit of foiling here. So foil this guy, foil, 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 and distribute. And don't forget that this guy applies. So distribute, and also distribute and distribute. So after I FOIL, I'll get 3 parentheses. This will be x squared minus plus 3x plus 3x minus 3x minus 9. Right? The middle terms will cancel. And then we keep going. This will become a minus x squared minus 2x squared, and then minus 6x equals to negative 12x. Again, continuing to distribute this 3, we end up with 3x squared minus 27 minus 2x squared minus 6x. And I'm going to go ahead and bring this over to this side, so I'll end up with a plus 12x equals 0. And then combining like terms, I'll end up with just one copy of x squared. That's combining this guy and this guy. That just gives me one copy of x squared. Then combining these two, I get a plus 6x minus 27 equals 0. So if I can think of two numbers that multiply to negative 27 but add to positive 6, how about x plus 9, x minus 3, multiply to negative 27 but add to positive 6 equals 0. Now by the zero product property, I know that this must mean that either x plus 9 equals to 0 or x minus 3 equals to 0. So we get two answers. Either x equals to negative 9, that's one solution, or x equals to positive 3 is another solution. Okay, so let's go back to the original statement. The original statement was this guy right here. So if we can come back and replace the x by those values, we can determine if we have a true statement. So we have 3 over x, 3 over x, and then it was minus 2 over x minus 3, and then negative 12 equals to negative 12 over x squared minus 9. Right. X squared minus 9. Okay, so we can check to see if in fact this is true. So it's 3 over blank minus 2 over blank minus 3 equals to negative 12 over blank squared minus 9. So let's check with a negative 9. So let's put a minus 9 there, and a minus 9 there, and a minus 9 there, and see if in fact we get a true statement. So that's going to reduce to negative 1/3, and that's going to be minus 2 over, that's going to be negative 12, and hopefully that's equal to negative 12 divided by 81 minus 9, (72), and then that'll reduce. So then that'll reduce, we have 8 and 9. So multiply this guy by 4 over 4. I'll end up with minus 4 over 12 plus 2 over 12. So on the left-hand side, I'll end up with negative 2 over 12. On the right-hand side, this will reduce. The 12 times 6, that's going to be equal to 1 over 6. So this is going to be equal to negative, this is equal to negative 1 over 6. Right? 12 times 6 is 72. And then this reduces to negative 1 over 6. And so this will reduce to exactly that, right? So this is true. Okay, and then what about the other one? If we focus on the other one, we've established that this one's a true one. But what about the other one? So we have 3 over blank minus 2 over blank minus 3 equals to negative 12 over blank squared minus 9. And so here we have a 3 that's going to reduce to 1. And here we're going to have a 3 that reduces to 0. Here we're going to have a 3 that's going to reduce to 0. And both of these cause a problem because we're going to end up with a 0 in the denominator. Right? So these guys reduce to 1 minus 2 over 0 is equal to negative 12 over 0. And remember that that means that these are undefined. Undefined, right? So it's not valid. That means that this is not a valid solution. So the only solution here is x equals to negative 9. Multiplied both sides by this. Good. Reduced. We got to that. Distribute. Combine like terms. We end up with this. Factors into that. We got the 3 and the negative 9. And then if we plug it into our equations, we see that the 3 causes a problem. We get undefines. And that the negative 9 works out well. So both of them give you a true statement. Okay, so negative 9 is the only solution. All right, what about something like this? Let's start off by simplifying this a little bit. Let's get rid of this root first, because otherwise, we can't solve for x. There's an x inside the root, in the argument of the root. So let's get rid of it. And to do that, I'm going to isolate it first and then square both sides. So the first thing I'm going to do is move things around a little bit. So I'm going to rewrite this in the following way. I'm just going to move this over to this side. So I'll end up with positive root 2 minus x. And I'll move this to the other side. That equals to 1 minus 2x. Right? Moving that over there. And then moving this over here. And now that I've done that, I'm going to square both sides. Minus x equals to 1 minus 2x. So I'm going to square this side, and then I'm going to square this side, giving me just a 2 minus x is equal to this guy squared, which becomes 1 minus 2x. I'm going to FOIL it all out. 1 minus 2x, which gives you 2 minus x is equal to, FOILing it out, we get 1 minus 2x minus another 2x plus 4x squared plus 4x squared. And now I'm going to set everything to one side, set it equal to 0, and combine like terms. So we get 2 minus x is equal to 1 minus 4x plus 4x squared. And then if I move this over to this side, I have to add plus x, and then minus 2 and minus 2. So I'll get 0 equals to negative 1 minus 3x plus 4x squared. If I now just move those things around a little bit, I'll get a 4x squared minus 3x minus 1 over here. 0. So I'll just flip it around a little bit and say it's 4x squared minus 3x minus 1 equals 0. So now let's factor that guy. I think because the numbers are so easy, we can just kind of use the guess and check method. It's going to be something that fits this form. Blank x plus blank equals 0. So we can just kind of guess and check different things. Because it ends in a 1, I know that the last term has to be a 1. So this is plus or minus something here, plus or minus something there. It seems like a pretty good bet that these guys are going to be 1s. And so now the first two terms have to multiply to this one. So 4, it could only be 2 and 2. So we can try 2 and 2, see if that works out. Play around with it. I get a 4, then I get a 2, and then either a minus 2 plus 2. That's not gonna work out. So let's try something else. The only other thing it could be is a 4. So let's try putting something like 4 and 1, and then playing around with it a little bit. So that'll give me my positive 4, and then that'll give me like a plus 4 or a minus 4, and then this will give me a plus 1 or a minus 1, depending on whether I choose plus or minus, and that seems to work. 4 and a 1, that can lead me to a negative 3. So again, just by guessing and checking different things, I think that the one that will work is going to be 4x plus 1 and then x minus 1. It's just a guess, so let's check it. That'll be 4x minus 4x, 4x squared minus 4x plus x. That'll give me that minus 3x and then minus 1. Good. So guessing and checking worked, because the numbers are so easy. But if not, we can also use the quadratic formula, right? So we can just go over to a equals to 4, a equals to 4, b equals to negative 3, c equals to negative 1. And then we can use the quadratic formula, x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then that will lead to our answer as well. But here, this isn't so bad. So then we can separate this into either that's equal to 0, which leads to 4x equals to negative 1, which means x equals to negative 1/4. 1/4 is one solution, or the other solution is x minus 1 equals 0, therefore x equals to 1 is the other solution. And remember, we got to check them, so we got to come back over here and determine if it's in fact true that these guys give us our answers. The easiest one to check is 1. So let's come back over here, plug a 1 for each one of those, and see if it in fact gives us the right answer. So let's put a check over here. Check, and we had 2x equals 1 minus the square root of 2 minus x. So let's see if 1 is in fact a valid solution. Right, here are my two solutions. So check if x equals to 1 is an answer. I'll have 2 times something is equal to 1 minus the square root of 2 minus something. If I put a 1 there and I put a 1 there, I get on the left-hand side a 2, right? These guys multiply to 2, equals 1 minus, and this will become 2 minus 1. That'll be root 1. Root 1 is just 1, so I get 2 equals to 1 minus 1, which is then going to be equal to 0, right? So this fails. I get a 2 equals to 0. That's a fail, right? Which means that this is not really a valid solution. All right, let's check the other one. The other one is going to be this. We get that 2 times blank is equal to 1 minus the square root of 2 minus blank. And I'm going to check to see if, in fact, it's negative 1/4. Negative 1/4 goes there. Negative 1/4 goes there. And see what we get. So this will reduce to negative 1/2 on the left-hand side is equal to 1 minus. That's going to be 2 minus minus. That's going to be plus. As a mixed number, let's do that. As a mixed number, it's going to be 2 plus 1/4, so 2 and 1/4 as a mixed number, which means that to convert it into a fraction, it's going to be 9 over 4. Negative 1/2 is equal to 1 minus the square root of 9 over 4. Or we could have gotten the common denominator, 4 over 4, that's 8 plus 1 over 4, that's 9 over 4, which then reduces. We get negative 1/2 is equal to 1 minus 3 halves. And 1 minus 3 halves, that is going to be true. Negative 1/2 is equal to negative 1/2. Right? 3 halves is 1.5 as a mixed number, so 1 minus 1.5 gives you negative 1/2. Great. So this one works out. This one works out. So this is the only true solution. X equals to negative 1/4. Okay, so when you run into situations where you have an equation and there happens to be a square root somewhere in there, one way to do it is to leave it alone, keep it together as a little unit, isolate it, and then you can square both sides so that so you can get rid of the root and then move forward, try and solve it. The only thing is you have to be real careful to check your solutions, because you might have sort of a phantom answer that results from the fact that you square both sides. Remember that when we square both sides, we run the danger of potentially making something that isn't true become true by the fact that we square both sides. So if at this stage, maybe this is equal to negative 5 and this is equal to positive 5, I square both sides, then I get 25 equals 25. I'll get a true statement after that. Okay, so that's why you have to check your solutions to see, to confirm that they work out. Okay, so let's see what the author did. Hopefully something similar. Looks like the author did something similar. Moved the 1 over, squared both sides. You get this, move everything into equal to 0, factored it, checked both of them. So the negative 1/4 works out. Both give you negative 1/2. And the 1, x equals to 1, does not work out. So when we solve equations, we may end up with one or more extraneous solutions, right? These are these phantom solutions that occur that don't actually solve the satisfy the original statement. Extraneous solutions may be introduced when we square each side of an equation, because the operation of squaring can turn a false statement into a true one. So if we started out with something that was false, like -1 equals to 1, but we squared both sides, we would end up with 1 equals 1, and that is true. So we can start off with something false, square both sides, and end up with something that's true. That's why we have to be careful. Okay, almost done. Last example. What if we had something like this? I like to call these quadratics in disguise. Remember, this entire section, for the most part, or a large part of this section has been really been focused on quadratics, right? Things that can be solved that fit this form. Ax squared plus bx plus c equals to 0, right? And so a power 2, that's a quadratic. We know a lot about this stuff. We can factor it. We can use the quadratic formula. And so this one here doesn't initially look like it fits that form because it's a power 4 instead of a power 2. But if we do a very straightforward substitution, like say a u substitution, why don't we let u equal to x squared, then that must mean that we can rewrite this as x squared squared, right? That's x to the 4th power, minus 8x squared plus 8 equals to 0. And now I can do this substitution where I let u equal to x squared, and I get u squared minus 8 times u plus 8 equals 0. And now I have a quadratic in disguise. This is going to fit this form. Fits with A, the role of A being played by a 1, that's a 1 in front, the role of B being played by a -8, and the role of C being played by an 8. So now I can use the quadratic formula. Now over here, by default, we use x a lot. So the variable here is x, so I just switched my variable to u. So now I'm saying that the solution to this is going to be equal to u, and it's that little formula. -b plus or minus the square root of b squared minus 4ac all over 2a. Quadratic formula. So therefore my u is equal to -1 times b, where the b is a -8. So I'll have this -8, -8, plus or minus the square root of -8 squared minus 4 times 1 times 8 all over 2 times a, which is a 1. Okay, so be careful that the b, this b has its own sign to begin with. The formula has a negative, but then the b came with its own symbol. So that's why there's 2 here. There's that sign that it came with, and there's another one, meaning that the u is actually going to be positive. So I'll get that u is equal to 8 plus or minus the square root of, and then -8 squared gives you a 64, and then 4 times 8 is 32. All of that gets divided by a 2. So let's put this up here. So that means that my u is really going to be equal to 8 over 2 plus or minus square root of 32 over 2. And we can factor this out. This simplifies. U equals to 4 plus or minus. Now the 32, let's stick it right in here. 32 is really equal to 2 times 16, and it's equal to 2 times 8, and it's equal to 2 times 4, and it's equal to 2 times 2. So 32 is really equal to 2 to the power of 5. So there's an invisible little 2 here. We can pull them out in groups of 2. And so we can pull out several of these, right? We can pull out a 4. So this is the same thing as saying that it's square root of 16 times 2, or 2 over 2, which means that my u is equal to 4 plus or minus 4 square root of 2 over 2. And pulling out that 4 is the same thing as pulling out little groups of 2 in powers of 2. Right? So that's the other thing I was pointing out, right? That this guy, we can think of it as root 32 is the same thing as root 2 to the power of 5, which is equal to 2, and then 2 to the power of 2 times 2 to the power of 2 times 2 to the power of 1. And now this turns into 1 copy of 2, square root of 2 squared. This turns into 1 copy of 2 out there. And then this one turns into another copy of 2 outside the root. And then we still have 1 copy of root 2 inside the 2. And so we end up with 4 root 2. Any way you want to think about it, either way. Or you can separate the 32 into 16 times 2. And so the square root of 16 is 4, and that reduces. Finally, back out here, this 2 will reduce with that one, giving me a 2. And we end up with u equals, so my u then equals 4 plus or minus 2 root 2. And we're almost done, except that the original question was not about u. The original question was about x to the 4th power minus all that. I'm the one that did this substitution, so we can't be done yet. We're going to have to come back and replace this here as well. So I'm going to bring this guy over and substitute it right in there. So remembering that u was actually defined to be this, that's how I did all of this. I end up with x squared is equal to 4 plus or minus 2 root 2. And so now when I solve for x, I'll end up with x equals to, well, let's take the square root of both sides. So I'm going to take the square root of this side and then the square root of that side, keeping in mind that I have to throw in the plus and minus. So it'll be plus or minus square root of 4 plus or minus 2 root 2. That's ugly. Let me zoom out a little bit. So we have several options here. This leads to several possibilities. So first of all, the outer layer of plus or minus leads to 2 possible answers. So I get x equals 2 root 4 plus or minus 2 root 2. Okay, that's one route. The other route is that x equals to negative root 4 plus or minus 2 root 2. And then each one of these lead to 2 possible answers. Either x equals to the square root of 4 plus 2 root 2, or x equals to the square root of 4 minus 2 root 2, or this one leads to 2 possible answers, x equals to negative root 4 plus 2 root 2, or x equals to negative root 4 minus 2 root 2. Okay, so we end up with 4 possible answers. We have this one, we have this one, we have this one, and we have that one. We can leave it alone like that, or we can convert each one of those into a decimal approximation. And then, of course, in order to check to make sure that all of them work, we'd have to come back over here, plug them in for x, and figure out if they are actually going to give you a true statement. Let's see what the author did for this. So he did a W substitution instead of a U substitution. So substitute it there. We end up with quadratic formula. We get the same answer here, plus or minus 4 root 2 over 2. Okay, so you get 4 possible answers, and then you can use your calculator to get a decimal approximation for them. Here they are. And then you should actually test them one at a time to really see if they really do give you the right answer. Okay, so that should be enough to get started on your homework in 1.5. Let me know if you have any questions.